The alternating series theorem helps us figure out whether an alternating series is convergent or not. Well, at least whether it is convergent. But like a lot of our other tests, it doesn't tell us what the thing converges to, right? When we've talked about infinite series, we've kind of thought, well, I could just add up a bunch of, like the first million of them or some million terms, and maybe that's a good estimate for the final sum. Is that really trustworthy? Well, think about it for the harmonic. If you add up the first million terms for the harmonic, you get a finite number, but really the harmonic ends up at infinity, and you're infinitely far away from the right answer if you just stop at the millionth term. So it's not overall a trustworthy idea. Let's apply it to something that you might say, well, of course, if the series is diverging, then just stopping at some finite number is not going to be a good idea. What if we use it for a series that's not diverging, that's converging? So let's use one of the nicer converging series here, or at least mathematically beautiful. So the sum of the reciprocal squares, it turns out that's equal to pi squared over 6, which takes a lot of math to prove that was a major advance back when it was found. And pi squared over 6 is about 1.6449. Interesting fact, if you end up taking a cryptography class and you're talking about primes and what's the chance that one number is relatively prime to another, if you just randomly generate them, that turns out to be 1 over this number. That's 6 over pi squared, which would be 1 over 1.6, so it's around 0.6 somewhere. So it's funny how that occurs in that problem too. Let's talk about estimating this number by just doing a finite sum. Let's say I was doing this sum, but I actually got lazy by the time I got here and just said, you know what, I'm going to stop right there. What's this sum? It's 1 plus a fourth plus a ninth. So this is my estimate of that sum, and it's equal to 1.36111111. Is that far off from 1.6449? I mean, it seems like it's kind of in the right neighborhood. Is it off by however much this is? This is 1/16, so that's equal to 0.0625. Can we say that my estimate is no worse off than the first term I neglected? Well, the error from this, so the error versus 1.6449 ish, I mean, that's not the exact number because pi goes on forever, right? Is about 0.28. So we might say, well, the first time I left off was 0.0625. Maybe that's just kind of how far off I am overall with my estimate. But we can see that how far off you are, even for a convergent series, can be a fair bit bigger than the first term you left off. But the magic is, if the series is alternating, then we can use this first neglected term as a bound on the error. So let's write that down. If it's an alternating series, and the alternating series test says it converges. Remember, there are alternating series that do converge, but that don't work with the alternating series test. Then the partial sums error is less than the first neglected term, like this thing here. Now, this error might be positive or negative, this error might be positive or negative, so it turns out you just say, well, take the absolute values of all that. How can we see that that's what's going on? Well, remember we had the partial sums in our drawing. They went like this, and each time the movement was less than the movement had been before, and that's really all we need to get this result. Another nice thing is that the final value of the sum so the final value, adding up all the way to infinity, is between any two recent partial sum values. So if I stopped here, I would know that the final value is somewhere between here and here. So let me kind of highlight those. It's between any non-recent partial sum values as well, but this is a tighter bound, right? Closer together. So this gives us an upper bound and a lower bound and tells us how much the error is. So that's a pretty good deal. The alternating series are really nice that way. Let's do a quick example. Let's say how many terms of what we're doing here, so -1 to the n-1 times 1 over n squared, do we need to get the error down to 1 in 100, 1/100th? Right, say if I need some value to within some kind of tolerance, it'd be nice to know how many terms I can add up to get to that, or how many terms I need to add up. Well, because this is an alternating series that converges under the alternating series test, we know that the error is the worse the error is the first neglected term. So we need the first neglected term that's basically 1 over n squared. We're ignoring the plus or minus part. To be less than 1/100th. So we're just saying 1 over n squared is less than 1/100th, which is pretty easy to solve. We get n squared is greater than 100, and so n is greater than 10. So 11 terms should do it, right? So does that mean I can estimate pi squared over 6 with just 11 terms? Well, this is not an alternating series. It doesn't work with what we just said. We were just saying the alternating version. Because that's not alternating. How could we get a bound for something like this since it's not alternating? Well, actually the integral test and the integral thinking about this integral is above, this integral is below because of the left-hand box method, right-hand box method. Integrating 1 over x squared is pretty straightforward, so that's what I would use to get bounds on that.